Hello, my name is Isabella, and today I'll be teaching you about the thermodynamics of a tropical cyclone, which is also known as a hurricane or a typhoon. Let's start off by first defining a cyclone. We know that cyclones are storm systems, but they're also known to be low pressure systems. So, for these, winds blow towards an area of lower pressure at the center of the storm system, where then air begins to rise upwards into the troposphere. So, as this air rises, the water vapor within it begins to condense and forms clouds and eventually precipitation. So, low pressure systems include storms, so they often are events of heavy winds, precipitation, or even snow, and these include blizzards, thunderstorms, and tornadoes. So, cyclones are a large example of these low pressure systems. Essentially, they are large scale convection systems that are driven by a temperature contrast between a hot tropical sea surface and also the cold top of the troposphere. So, they're often characterized by their noticeable low pressure center, often referred to as the eye of the storm, and an inward spiral convergence of strong winds towards the center. So, tropical cyclones are known to represent some of the most violent of all storms, with their really high wind speeds, storm surge, and extensive land damage. So, before we begin connecting cyclones to thermodynamics, it's important that we understand the basis of both laws of thermodynamics and also entropy that tropical cyclones are defined by. So, the first law of thermodynamics states that energy cannot be created or destroyed, therefore, it's always conserved. And the second law states that for any spontaneous process, the entropy of the universe will increase. So, entropy, as we know, is a measure of the energy randomization or energy dispersal of a system. It's also a thermodynamic function that increases as the number of energetically equivalent ways of arranging the components increases. Therefore, more random systems will require less energy than ordered systems. So, what's important to note for cyclones is that the macro state with the highest entropy also has the greatest dispersal of energy. Therefore, the kinetic energy will be distributed. So, although they might not be noticeable in still pictures, there are many interconnected energy systems found within a cyclone. First, tropical cyclones normally develop with a few days of a feedback supply of mechanical energy when that sea surface temperature is above 300 Kelvin and the horizontal scale of circulation exceeds the critical radius of around 50 kilometers. So, this mechanical heat energy generated from the sea surface and atmosphere temperature difference is then stored within the density distribution of a cyclone as potential energy. This all occurs because of atmospheric circulation or the large scale movement of air with ocean circulation, which then redistributes thermal energy along the Earth's surface. So the potential energy within the system is then converted into kinetic energy of the circulatory motion of the atmosphere. So this kinetic energy is then dissipated into internal energy through turbulent drag force. And this last energy transformation occurs mainly in the boundary layer of the cyclone near the sea surface. So, although energy is transformed through this process, it's conserved and never lost. Therefore, it follows the first law of thermodynamics. So, because of this law, scientists can assume that the net generation rate of mechanical energy is always going to be equal to the rate of increase of kinetic energy for a cyclone. So, the thermodynamic cycle as a whole is super crucial for extracting energy from the ocean to drive this mechanical energy generation required for the development and continuation of a tropical cyclone. So, for those who are in the field of atmospheric and ocean sciences, it is well known that a strong vertical wind shear can have a really great effect on the intensity of tropical cyclones. So, from a thermodynamic perspective, the impact of vertical wind shear concentrates on the constraint of heat energy by low entropy from the environment. So, there are two different ways in which a vertical wind shear can constrain the intensity of a tropical cyclone. First, there can be a decrease in the entropy surrounding the eye wall or the center of the storm through something called the radial eddy flux. Radial eddy flux is a covariance between an instantaneous deviation in both wind speed and also gas concentration at the mid level of the storm. Secondly, low entropy air can be flushed out into the boundary layer by a downdraft outside of the eye wall. So, the stronger the magnitude of these forces, the more distribution of heat occurs, and therefore a decreased entropy and cyclone intensity. So, alongside this wind shear, the entropy difference along a cyclone's eye wall plays a very important role in determining the storm's overall intensity. So, the heat flux received from the ocean cannot fully offset the low entropy downdrafts before air reaches the eye wall. This causes a decrease in the overall entropy of the eye wall and therefore a distribution of the cyclone's heat source. And with less energy, less kinetic energy is generated, and the cyclone intensity is also decreased this way. So, the principle of maximum entropy production is known to be the tendency to increase both the generation and dissipation of available energy. This can be seen in many non equilibrium phenomena, which include cyclones. Experts have found that tropical cyclones tend to develop towards states with higher rates of dissipation through their feedback growth of dynamic motion. This causes the cyclone size to exceed its critical value, determined by the correlating non-equilibrium state. So, in these states of non-equilibrium, tropical cyclones are able to develop in a way that recovers their stability by reducing their available energy and therefore producing more entropy. So, through this analysis, scientists have found that tropical cyclones tend to move along trajectories with more energy dispersal and randomness. Therefore, they move along courses with higher rates of entropy production. So, thank you for listening to my presentation on the importance of thermodynamics on cyclone formation, duration, and intensity. I hope you were able to learn something new today. Thanks again.